first speaker this afternoon is Alex Tovbis from the University of Central Florida, and he's going to speak on the spectral theory of soliton and breather gases for integrable equations.
Thank you, Peter. And I want to thank the organizers for inviting me to give this presentation. So I will be talking about spectral theory of soliton and breather gases for integrable equations. So breather can be probably remove this word, and it's okay. So I want to acknowledge my collaborators. There is a list of them of my collaborators which were participating in one or another part of this project. And now this is a picture of circular condensate gas, courtesy of Stefan. Right? Okay, it has. Well, maybe we will get to the circular condensate, and I can give some explanations. So, because it's let me first say a few words about how should we understand the words soliton gas. So when we consider soliton gas for an integrable equation, we can think that we take a large collection of n solitons, so n soliton solutions, maybe with some special arrangements, and then consider a limit when n goes to infinity, and study the properties of the of the objects that will get this way, right? That's one school of thoughts. I can mention Dichenko, Zakharov, and Zakharov, primitive potentials, and then recent work of Tamara, Ken, and Bob, and co-authors that is ongoing as far as I know. Well, the other way of looking at the same phenomena is to take a finite gap solution to the NLS and start to squeeze the band so they will become very small, simultaneously increasing the number of the bands. And if that is done if the limit is done in the right way, which is called thermodynamic limit, and which can be in the form that we know now, formulated by Gennady L. in 2003. So that's another way to consider a sort of spectral theory of soliton gases. There are various applications. So the goals of my talk today would be to give which are sort of, given 30 minutes, a little bit self-contradictory because it's really hard. So it's give a brief review of derivation of this equations of the soliton gas, and I will be talking today only about equilibrium gases. So the gas doesn't have any x and t dependence, so it's the same at every point in the xt plane. The properties of the gas are the same. That's what I mean. And also introduce some new results. But the review of the derivation I would like to make in terms of the Riemann surfaces only. So that there will be no, of course, there is in the background NLS equation, but I will try to use the language of Riemann surfaces for the derivation. So let me start from the end. So what are the finite product that I want to get? I want to get the two functions, u of z called density of states, and v of z, its temporal analog, sometimes called density of fluxes, associated with a given gas, right? So how should I understand this? What's the meaning of these two functions? One is the remember, I'm talking about finite gap solution taking in some limit. So one is the density of wave numbers, which are so to say continualized all over the spectral set of the problem, and the other is the density of frequencies. So these are the quantities that I'm looking for, and so I will give a way to derive. I will show a way to derive these equations. Number two is, so once you have this equation, so if you if you take the ratio of V over U, it's like a wave number over frequency. It gives you effective speed of the element of the gas. And so if you just multiply first equation by S of Z and subtract from the second one, after very few simple algebraic calculations, you will end up with equation of states that we've seen many times on this conference, which relates initial speed of the free particle or free soliton or breather or whatever it can be as 0, effective speed of this object in the gas, and density of states. Right, so these quantities are related. So if we will be talking about non-equilibrium gas, there is another equation that U sub t equals S U sub x, right? And there are some from that you can derive some equations for this sigma. For this function sigma, very important. But again, I'm considering today only equilibrium gases. So finally, this is a equation. So these equations are called, by the way, nonlinear dispersion relations, and I'm considering them for NLS. But of course, if you replace simply minus z bar with plus z, you will obtain the equations for KdV. Soliton gas, as was derived by Gennady in 2003. Okay, so what is the to illustrate the meaning of the last equation of this equation? We can imagine that we have a soliton which is big to that we can see it, and then the gas. And the soliton, of course, has a free speed. So if it runs with its free speed, after some time it will be here. But because of the interaction, speed is different. So the big soliton grabs the small one, push it back, and get some momentum itself. So the speed will be a little bit faster. So the effective speed will be this distance divided by the time. Okay, so by the way, the picture was taken from the paper of Gennady in 2016. So again, other than discussing how the NDR were derived, there is a question of existence and uniqueness of solutions of integral equations, some special solutions, generalizations, and so that is as much as I can. I will go down this program. So let me start with, so this is the NLS equation, brief reminder. It has some special solutions. One of them is the famous soliton solution given in this form. There are also breather solutions. There are also finite gap solutions. So, and gases is a randomized large ensembles of special solutions. Now, we will be talking about finite gap solutions, without, of course, introducing them, because time doesn't allow to that. But finite gap solutions are defined by underlying hyperelliptic Riemann surface. And so let's take spectral bands associated with a given finite gap potential. Right, so in the nonlinear Schrödinger equation situation, there is Schwarz symmetry. So there are bands gammas, and there are gaps between them, shown in red. And one band is of a little bit of different nature because it intersects real axis. We will be shrinking these blue bands in the process, so that and insert new bands. So everything will be accumulated on a compact. For example, this curve, but not necessarily, can be two-dimensional compact. But Schwarz symmetry is the necessary condition. Okay, so now, as I said, I will skip finite gap solution, and also I will introduce cycles, pretty much as shown here. A cycles and B cycles. They're up to sign. They form a homology basis. So now when we have a Riemann surface, hyperelliptic Riemann surface, we can talk about various meromorphic differentials. right? If you want to think about, don't want to lose at this point a significant part of the audience. So I would say that think about, if you know what is that, great. Otherwise, think about some function defined on the surface and dz at the moment, right? So these differentials can be uniquely defined if you state their singularities, and the singularities are at. So we have a hyperelliptic Riemann surface. That means two-sheeted. So we have two infinities on one sheet on the other sheet. So we define the behavior as plus minus one plus smaller order terms on corresponding sheets. And this is quasimomentum, dPn. And this n denotes the number of the number of bands in the upper half plane, strictly in the upper half plane. So the genus is 2n in this setting, right? And for dqn is that. That's and there are no other singularities. That's not enough to uniquely define the differential. But if we require that they're real normalized, so all the periods, integrals over any cycle that you can think about is real. So then it is uniquely defined. Now, once we are done with these differentials, we can define wave numbers and frequencies as simply the periods of these differentials, right? As shown here. As you see, some periods, because of the so this of course this period should be real because they're real normalized, right? And because of the Schwarz symmetry, if you take symmetrical band, so the corresponding wave numbers should be the same, right? But we have two kind of wave numbers and frequencies. One is tilted and the other is not, and you will see distinction in a moment. So right now it's a cycle wave number or b-cycle related wave number. There will be distinction in a moment. So once we have this, once we discuss the wave numbers and periods, I want to remind you that any differentials, two differentials on the meromorphic differentials or second time meromorphic differentials satisfy this Riemann bilinear relations, right? And so what I want to do, I want to take this dp and stick it here as one differential, and as another one, I would like to put normalized holomorphic differentials, two n of them, all of them. And that will give me, if I do so, that will give me this system of equations. And that is where I start to work, basically, this system of equations. So what is this system of equations? So again, input information is only Riemann surface, right? Nothing like that. And the differentials that I chose, that's it. So what are these? This differential right here is the normalized, is the J's normalized holomorphic differential that you can think about as a polynomial of degree 2n minus 1 divided by the radical r. Radical is this. So it's a product over all the z minus every n point that you've seen on my picture. And they are defined by the condition that over the period over Wj over cycle AM is delta Mj, Kronecker delta, right? That's how they define. They define uniquely. So this system of equation is uniquely defined. Okay. Now it's worth to mention that you can see it as a system of linear equation after all. Right, this is a system of linear equation. The number of let's count the number of variables. So how many equations? We have 2n equations. How many unknowns? We have n these unknowns and n this unknown. So the count matches. So at the next step, what we can do, we can actually take real and imaginary part of the previous system. Now, k's and omegas are real. All are reals. Integrals, of course, are not. And so if we take a real imaginary part, so imaginary part give us this system of equation. And the real part is it's actually not a system of equation because it's expression for these tilted quantities, wave numbers and frequencies that corresponding to B cycles in terms of the remaining one. So the strategy is you you first solve this system of equation. You got Km or Kj, and then you just recover tilted wave number and frequencies. I'm talking now mostly about the results that from my paper with Gennady of 2020. And so it's right here we can already see that those wave numbers and frequencies called solitonic should approach zero if we shrink the corresponding band. And why this is happening? Because this integral will grow as a band is shrunk, one particular band. And so for the corresponding, in order the everything else stays order one. So in order to the balance to be there, the corresponding k should go to zero. So that's very simple. But those guys do not necessarily go to zero. Okay, so the system of this equation for KdV was given in the paper of Flaschka, Forrest, McLaughlin, but there was no analog of that part for KdV, and that is true as we will see. Time permits, unless there is a residual background. If you have a residual background, so you are looking for a soliton on the cnoidal background or more complicated background, you will have then this type of relations as well. So now I want to go to the thermodynamic limit. So that is a way. So it's a description how large genus limit is taken in this situation. So I already assume that the bands are small. So if I take the endpoints, average of endpoints, call it Zj, I can assume that this is the center of the band, right? Although if the band is a curve, that's not true. But because they're small, okay, let's do that. Delta J is half the size of the band, and then we take a limit when all bands or all except a few bands are shrunk. In which way, right? So they are shrunk, and at the same time the number of bands is increased, so they accumulate on a certain compact set. Let's say in the upper half plane with a certain density. So phi of z is a probability density function on the compact that will be accumulation set. Now we assume that the center of two bands keep the distance 1/n from each other. And then the question is, okay, so how fast do the bands shrink? Again, it's at our disposal. So for exponential or standard spectral scaling, we assume that this is just e to the minus n times some positive coefficient, right? Then, of course, there can be other scales, sub-exponential and sub-exponential and super-exponential. Super-exponential corresponds to the ideal gas, so that means interactions are negligible, and sub-exponential corresponds to the condensate. So there are only interactions basically that we have to take into account. Now there are also, we can say, soliton gas again when all bands collapse, shrunk. Breather gas is when one is left, and that one provides a background, plane wave background, and then elliptic gas when you have elliptic background, and so on. One can go on. So the questions that I would like to address is what is the thermodynamic limit of these wave numbers frequencies for soliton and breather gases, for elliptic gases, and what is the thermodynamic limit of differentials themselves. Right? Okay, so delta will be the maximum of all small deltas. And then so in order to answer this question, I first need to find asymptotics. Remember, I had a system of linear equations, right? And the size of the system was growing, and I have to know something about the coefficients of this matrix. So this lemma which I obtained with my postdoc Fudong Wang, gave some leading order answer. What happens? It looks complicated, but this is for breather gas, by the way. But if you forget about breather, everything is shrinking. You can essentially keep only this red term in the brackets. Then it's more manageable. So you see that off-diagonal terms have order 1 limit, whereas diagonal terms of the system, right? So diagonal elements of the Riemann period matrix, they have order like 2 logarithm of modulus of the size divided by minus I pi, right? We will calculate that down the road. But then what we do, we take this leading order behavior and plug it into the system, and then I will show you what. So we plugged it in again. Disregard this breather term, so we get this type of equation. So what is U? U is because of the lack of space, I wrote it one equation for both wave numbers and frequencies, depending what you put in the right hand side. Here you get either equation for k or for omega. And so let's look at this term that was that corresponds to the diagonal, right? So you take a logarithm of shrinking band, and you recover the power of the n you had in the exponential with a coefficient, right? Okay, and that's the other order, and that's what other order terms give you. Now these terms are essentially of order 1, and there are n of them. So this term is of order n. So if we want to have balance of terms, so this term there should be this just n here, right? Just exponential. Okay, then the terms are of the same balance, of the same order. And if I assume that u, which is km, is something order 1 over n, right? So then this n and this n cancels, and over here 1 over n goes in front of integral, and I get some integral equation. If, however, s is bigger than 1, for example, this s, for example, 2, right? Then this term is of larger order than that one, and then this interaction doesn't contribute. We have ideal gas. And if s is 1/2, then this term doesn't matter, and we have what we call the condensate, right? So so now, so rewriting summation as an integral, we get this equation. So that equation which that I started my talk with for u and for v. And there is a question. So how you express u? So we had this rescaled wave numbers were called u hat of z given at point. You interpolate them, multiply by this density function. So when you go to integral, you have to take into account how your centers how they accumulate, and that gives you u of z, v of z, and sigma becomes this quantity, where nu is this coefficient in the exponential, telling you how fast the exponential is shrinking. Okay, so now we have these equations. Now the question is, okay, solutions, existence, uniqueness, whatever we can say. Now I want to emphasize that these equations are Fredholm equations, Fredholm integral equations. Of which kind? Well, it depends on sigma, right? If sigma is 0, it's a first kind. If sigma is separated from 0, it's a second kind. If sigma is a mix, it's a third kind. So the question is not completely trivial of solving those equations. So with Arne Kullers, we found that under some mild restrictions on both gamma plus and sigma, because this is our input information. Gamma plus and sigma. That's what the remnants of the sequence of Riemann surfaces that we see now, right? Only that. So based on this, if it is reasonable, if the compact is not weird compact, right? So we have there exists a unique solution for each of these equations. Moreover, solution of the first equation is non-negative, which is essential, because negative density of states doesn't make any sense, at least at the moment. Okay, so I'm done with this, and let me go to the next point, which is average densities. So now I can calculate conserved average conserved quantities. So how I do it? So essentially, I'm calculating coefficients of the expansion of infinity of this differential dPm, right? I call them IMN. Okay, that's what I want to calculate. And the theorem says that you can, in the thermodynamic limit, when n goes to infinity in the prescribed way, there is a formula for them, so you can express them through this integral. This is for breather gas, but disregard it, please, at the moment. So what will, and we provide error estimate. Now, what happens if we take now n, if we fix m and take n goes to infinity? So, right, so that is true for large n. But now I want to take a limit as n go to infinity. Then, of course, this sum goes into integral, and we recover this simple formula for the limiting m's average conserved density. Just that. That's NLS, but KdV is very similar, and the average fluxes will be very similar. Moreover, if we assume, now that is true, of course, we need to take assumption, we need to assume that the counting measure, weighted counting measure, where these are wave numbers put there, converges, weakly convergence to this measure, u d lambda, where lambda is the reference measure, which is arc length if your object is one-dimensional, or area if your compact is two-dimensional, or whatever is the case. Now, if we additionally assume something about this convergence, where is that? I cannot find. Yeah, accuracy is this. Then we can say something about accuracy of that convergence. Now, okay, let me go to the next slide. So now, once we know what is the limit of IMN, why not to stick this limit to the series here? And whatever I get, I want to think about it as a limit of the dp dz, as a limit of this quasimomentum differential, for example. Okay, but I have expression for im. So if I stick this expression into the formula and do some simple algebra, then I end up with this simple relation to dp dz. So at the end, so here for simplicity, I took a bound state. So the set gamma is on the imaginary axis, right? So so as you see, dp dz is just 1 minus Cauchy transform of your density of states. Now, in general case, you have to tweak u, put some geometry of the curve. Now we're talking about the curve. Not about two-dimensional set, and we get this expression. Finally, I have 2 minutes. Or... Okay. I will just flash then. So I skip some certain things. So now I want to mention another class of soliton gases related with the periodic what I call periodic soliton gases. So you have here, you have some function q of x. You assume that this is your potential for the semi-classical nonlinear Schrödinger equation, right? So you take a semi-classical limit, you see potential has this form, then one can argue that the bands and gaps will obey these requirements of the thermodynamic limit. And we can calculate that the density of states is the density of centers is given by this expression, nu is given by this expression, and so the sigma, we have expression for sigma, and then in this case we can calculate u, the density of states. It is u is proportional. It happens that, oops, why I'm going in the wrong direction. happens that density of states is given by this formula. So it's proportional basically to the density of density of bands. This is the theory. Okay, thank you. I have to stop here.
Okay, thank you very much. I think that perhaps there might be time for one very quick question. Okay.
Thank you. Yeah. So you have a theory which is like soliton gas, but purely based on Riemann surface.
Yes.
So can you extend that to other Riemann surfaces, like n-sheeted Riemann surfaces, and perhaps other differentials with different asymptotic behavior at large?
Other differentials for sure.
Yeah.
Other Riemann surfaces. That's a good project. Sound to me, but right now I don't know. But I don't. It would be much more complicated, but I don't see why it cannot be done.
Yeah.
Okay, thank you very much. Let's thank Alex again for his talk.